Good evening, everybody. We're very happy this evening to have David Kaneda with us from Integrated Design Associates Incorporated from San Jose, California. David has been here today working with the Architectural Engineering and Construction Science Advisory Committee, and he's graciously consented to talk about his work, and he's going to talk about moving toward a zero-carbon future. The idea is Z-squared design facility, Z-squared equals zero energy, zero carbon emission, and I think this is going to be interesting. It relates to LEED buildings, and so David, thank you for coming. We look forward to your presentation.
Thank you. Can everybody hear me okay? Yeah? Okay. The first thing I'm going to do is just play a short video clip that this group called Actera did about the building. So it actually gives you a little bit of a better idea of what the building's about, and also kind of has video of the inside of the building so you could get a better sense of it. But the sound's playing out of my laptop, so it's not going to be really, really loud.
Example of maximizing the sustainable built environment. Our business is designing electrical systems for buildings, and we specialize in sustainability. This building was originally a branch bank. It's about reusing things. It's about reusing the building to start with.
We just thought it's a pretty cool looking door and feature of the building, so we didn't want to throw it away. The building is a very unusual building. It is designed to be a very, very high efficiency building, and it's also designed to have renewable energy on it, so it should be a net zero energy building. And what that means is over the course of the year it uses net zero energy off the grid.
The building generates all the power that it needs through the use of photovoltaic or solar cells.
We produce an equivalent amount of energy to what we use. We believe that makes the building a zero carbon building also because we disconnected the gas meter, and so we produce no carbon dioxide. But at this point, the meter is spinning backwards.
To the best of our knowledge, we're the first commercial net zero energy building in the nation. Building with a geothermal heat pump, and pump actually extracts heat from the ground and transfers it to the building in the winter. In the summer, it works in reverse. You could put in blinds. We've elected to use a new technology called electrostatic glass, which blacks out and basically reflects the light. So there's 15 skylights. They were all cut into the existing ceiling and roof.
You don't have to be Adobe. You don't have to be Google, you don't have to be Cisco system to put some PVs onto your roof, or when you renovate your building, look at the energy issue, look at the green issue. It makes a lot of business sense.
We welcome visitors to come. We arrange tours. There's been various groups that have been through the building.
We're more than willing to share the techniques and kind of our trade secrets, as it were, with other engineers, because there's a lot of buildings that need to be designed. We're only ever going to be able to do a small fraction of them. So the way really we can leverage kind of what we've been able to do is by teaching other people to do the same thing, so everybody has the ability to design green buildings. So as far as I'm concerned, the faster it changes, the better. Okay, so
What I'm going to try to do is just pretty quickly run you through what this building's all about. You guys are all interested in sustainability. That's why you're taking this class, correct? And just out of curiosity, what are your majors? Just kind of yell out.
Landscape architecture.
I think we have some architectural engineers here as well.
I am.
Okay. I'm just curious. It's interesting. We're in the middle of the Silicon Valley, San Jose, and there's like all of the above working on these types of issues. It's interesting. There's a huge amount of money right now going into they call it green tech. I'm doing a house for a venture capitalist right now, and it's one of the bigger firms in Silicon Valley, and all he does full time is he's searching around for green technologies that they judge are worth investing in, and they control hundreds of millions of dollars. So it's become a very big thing. So So this is just a quick overview of what I'm going to talk about. It's probably interesting just to kind of hear about how we decided to do this project. And then what I'm going to go through is just kind of the key concepts and ideas that we use to try to get this building down to very low energy use and very high efficiency. And we'll talk a little bit about how much energy it uses. And a key thing is the photovoltaic system that provides the energy for this building, and a very important piece of that was how it's paid for. A lot of the money came from federal tax credits and a state rebate. And so I'll kind of go through the math on how much it actually costs us. And then just go through a little CO2 calculation because I think that's interesting. So this is the building when we bought it. So the architect that we hired to do this described this as the ugliest building he's ever seen. And it is pretty ugly. So the way we even got into this was my wife's also one of my business partners. She's an accountant, a CPA, and we had sold a house in the Bay Area. And you have to understand that property in the Bay Area costs a fortune. So to the tune of like a regular house like you'd find around here will go for like 1.2 million. On maybe an eighth of an acre or something like that, or a quarter of an acre. So we sold this house and we literally cleared like $500,000 or something like that. And so there's this wrinkle, and it was rental property. We had bought it as a second house and we're renting it out. So there's this wrinkle in the law that says if you buy another property right away within 3 months, 90 days or something like that, you don't have to pay tax on it. Otherwise, you have to pay tax on it. So, calculate the tax on $500,000, and it's not chump change. So we bought this house and we flipped it, and we decided I've always wanted to, put some cool stuff into the office I'm working in. But you never want to do it when you're renting a building. You want to do it when you own the building, because then if you improve the building, you get to keep it. So we decided we were going to buy a building and use this money that we made off the house that we sold as a down payment. And it's a long story. We were looking around and looking around and looking around and running out of time and looking around. And I wanted something with a high ceiling because I had some ideas on how I could increase the value of the building. But eventually we stumbled on this building. It had all the things, other than being very ugly, it had all the things that we thought we needed from a size standpoint, from a ceiling height standpoint, from a big issue is from a parking lot standpoint, it turns out, because office buildings need a certain amount of parking based on the number of people that are going to be working in there. So it had all that stuff. And like I said, also I was running out of time, so I'm not a professional developer. If I was, probably before I sold the house, I would have found a building to buy. But anyway, like I said, I'm not a professional developer, so I didn't figure that out. So kind of we were like running out of time and panicking because there was like a lot of money on the table. So this is what we ended up with. So my company designs buildings. We do the electrical systems and the lighting systems, and our specialty is green buildings. So we decided that we wanted to do something that would be an example or kind of exemplary for what show what we believed in, right? So I mean, I feel bad if I have my own building and I'm telling people that they should spend, you know, enormous sums of money sometimes to do kind of cutting edge green buildings, but then I'm not willing to do anything myself when I have my own building. So we thought it was important to walk the walk, not just talk the talk. And then the other thing is that you need to realize when you're designing these buildings, you're trying to make all the systems really kind of optimize everything so it works perfectly together. And so, you know, I describe it as like trying to design it's like a Swiss watch. You don't, you know, have like 5 people design separate gears and then try to jam them all together. You kind of have to design it as a piece. So that's a really key thing with integrated design. So, like I said, fortunately I'm in the business. Fortunately I get to work with a lot of the best players in the industry. And so, fortunately, I know who's really good at this. So I picked this team of an architect, mechanical engineer, structural engineer, contractor, etc. And I guess the key players were the mechanical engineer, the architect, and then ourselves as the electrical engineers, because those are the people that kind of have the biggest impact on the energy use of the building. So this is back in September of '05. So this is before Al Gore's movie came out, An Inconvenient Truth, and before all the hype on global warming and carbon dioxide and greenhouse gases. I had heard some talks by a Stanford professor on it, but it didn't have all the hype that it has now that everybody's talking about it. This is back at the time when green buildings was becoming the thing that everybody's talking about, and there's this new standard called LEED and this group, the U.S. Green Building Council. And at the time there were like 10 LEED Platinum projects in the whole world, or 12 LEED Platinum projects in the whole world. So I thought, if I want to do something that's really makes a statement, I want to do a LEED Platinum project. So we went in and we had this meeting the first day when we started this project at the architect's office, and the guy's name's Scott Shell, and he says, David, you're the owner, what are your goals for this project? So I said, I want a great place for my staff to work, a place that's really fun and pleasant to work in, and I want this building to be really green, and we actually want to look and see what it will take to get to LEED Platinum. And how much is it going to cost? And of course the architect, being an architect, said, that depends. And so we started this project off and started kind of sitting down and brainstorming about, I think I could do this and I think I could do that. And, it started at like 8 in the morning, and at like 10 in the morning, the architect suddenly steps back and says to me, he goes, I have an idea. What if we kind of make this building, beef up the insulation and kind of make this building into a super efficient building? And then what if we make it all electric, disconnect the gas line so it's got no gas connected to it, make it all electric, and then put photovoltaics on the roof and put enough on that it offsets 100% of your use through the course of the year. If you do that, you'll be net zero energy and you'll be zero carbon emission. And he said, I don't know of any, big buildings other than like, small cabins up in the mountains that can make that claim. Now, we could call it, Z2 or Z squared or something like that. So I'll be honest. When he said that, I actually thought, what the hell is this guy talking about? Is he nuts? Because I was like really focused on that LEED platinum goal. That was like the standard that I wanted to go for. I was like, this guy's like way out in left field. But the one thing, I've worked with this guy before, that's why we chose him. And the one thing I know about him is he's really forward thinking. And when he says something, you really need to take it seriously. So I said, okay, I'll think about it. Let's keep going on the design and let me think about it a little bit. So that was on like a Thursday, and I said, let me think about it over the weekend. So over the weekend, I'm talking to my wife about it. And the point she made was that, look, when you guys do these buildings, and we had just completed a design that was trying to get to LEED Platinum, and in fact did get LEED Platinum eventually. And she said, when you do these really green projects, what is your role on the design team? What are you trying to do? And the answer was, we're trying to go after the energy, right? The high efficiency. So she said, well, if you do what he's suggesting, it focuses on the things that your firm does really well. So if you want to like show off your commitment and what you're good at, then it makes sense to do it. So she convinced me. We came back on Monday, decided we're going to go for net zero energy, zero carbon, and that totally changed the project because instead of doing things like, looking at recycled materials and FSC certified wood and low VOCs and those types of issues, the majority of what we focused on was energy. And so, we did things that wouldn't get us a LEED point, but would get us less energy use. And then we didn't actually go back and look at LEED till the very end of the project. So this is just some background information. Buildings are responsible in the U.S. for roughly 40% of carbon dioxide production. And when you add in the creation of cement, which they use coal or gas to burn gypsum, that goes up to almost 50%. It's like 48% or something like that. So roughly half the CO2 in the U.S. is generated is attributable to buildings. And then, if you've seen An Inconvenient Truth, you've seen half these images. But I put them together before I saw the movie, so. There's starting to be this body of evidence that global warming really is happening, that it's happening faster than we thought it was. The good news for you guys is that if this actually happens, you'll be able to get down to the beach in half an hour drive instead of having to fly there. So here's some of the concepts that we used in the building. And I'm not going to go through all of these, but I will go through a number of them. These are the architectural, structural, landscaping concepts that are used in this building. So the first one is we just reuse an existing building. So there's a lot of buildings that just get knocked down, and so all the embodied CO2, all the labor that went into it, you just toss it into the dump. It becomes landfill. It pollutes. It's much better if the building's reasonably robust if you could reuse it. So that's one of the things that we did. And it was, the interesting thing is if you look at these two photographs. Obviously, that's a before shot. You can see how dark it was with the lights on, and you can see how light it is now with the lights off. So basically, in this building now, the lights are off from about an hour after sunrise until or maybe half an hour after sunrise till about half an hour before sunset. unless it's like a really rainy day or something like that. The lights are just off. It's a very pleasant place to work in. It's comfortable. It's a fun place to work. We have a foosball table, and they actually talked me into putting a bocce ball court out in the courtyard. So it's amazing that these guys get any work done. And then one of the things that we did is there's kind of this emerging body of evidence that says if you give people views out, it actually kind of increases your feeling of well-being. There's kind of windows cut into the side of the building that give you tremendous views out kind of to the east, and then to the south there's this bocce ball court. It's in a courtyard. We just planted kind of a screen of bamboo, so you kind of be looking out into this nice courtyard with bamboo. Now the interesting thing is, if you actually, I don't know if you guys are familiar with the LEED scorecard, but there's actually a separate point for daylight and a separate point for views. And interestingly enough, the way the architect designed this building, the kind of vertical glass on the sides of the building, which is this window here, and there's like a lower sliding glass doors along here. Those are more or less just for views. We, of course, do get light through them, but you could block those up and we'd have plenty of light in the space. And the daylight all comes through skylights up in the roof that let light transfer down. Oops. We went through this interesting discussion of, do you put in clear, do you put in diffuse skylights? And everybody, I actually got yelled at by this woman in Sacramento who's like the authority on daylighting, and she's like, what the heck were you thinking? Why did you put clear glass in your skylights? So it's kind of common knowledge that you don't do that, but we did it. And it's a little bit of a problem. You can see here, this is one of my staff, and it's the sun shining down on his shoulder. You can see glare on his screen. It's a little bit uncomfortable. That's my office there. The light's hitting the wall. But in fact, first thing is, it's at any one spot, at any one desk, it's about when it hits your desk, it's about a 15-minute problem, it turns out. And then it's a problem for about a month, and then it's somebody else's problem because the sun keeps moving around the office. So like different times of the year, it only hit the same spot for a short period of time. And so one of the things is, we knew it was going to be a problem. We actually had a long discussion about how do you mitigate that problem. Do you put, kind of gauzy cloth underneath the skylights? Do you put milky skylights in? Do you do this? Do you do that? And none of the ideas that we came up with we liked, because you would lose view of the sky, or it would change the color of the light and things like that. So eventually what the architect said is, look, you're going to live in this building, use it as a lab. You got 9 skylights, well, you have 9, 10, 11, 12 skylights in that room. Do different things on different skylights and see what works. So we're starting to do that now. So right now we've got like this white kind of all-weather cloth on the outside of one of the skylights to see if it'll help, and it doesn't help at all, it turns out. But we're trying stuff just to see what works. And when we put that in, the guy that sits under it, he hates it, and he said, I'd rather have the sun beating down on my head for a couple minutes a day so I can look up and see blue sky. So it's kind of interesting. So that's what the skylights look at if you look straight up into them. We used, nowadays there's really good glass that's called spectrally selective glass, and what it does is it blocks a lot of the stuff that, it's electromagnetic radiation, but you can't see it. So as you get out of the visible spectrum, like the infrared and the ultraviolet, it blocks a lot of that, but it lets through as much light as possible. So the glass that we used up on in the skylights is something called SolarBand 70 XL, which is kind of the best performing kind of standard glass that is out there right now. Oops. And then on the windows on the side, then the issue is that you get sunlight beating in and that's not doing that much for you from a daylighting standpoint. So you actually want to control the light when the sun's trying to come in the side windows. So on the east side here, we put in this stuff called electrochromic glass, which is this really cool technology. You put an electric charge on it, and it darkens down like photogray sunglasses and changes the property of the glass. So it goes from like 50% transmittance to like 4% transmittance. So it blocks that light from even entering the space. It doesn't even get through the outer pane of glass, which is really cool because, you know, if you put blinds in, the problem with blinds is it's already in the room and you're trying to bounce it back out. So a certain amount of it gets trapped inside the glass and heats up your space. The problem with it is that piece right there is a $16,000 window. So even though it's cool technology, that was like the big splurge, you know. It's like, oh, we really like this, we think it's cool, but realistically, until the price comes down, this is the only project we've ever used it on. And then on the south side, they just designed a pretty simple overhang that if you kind of look at sun angles, it blocks the sun in the summer, and then as the sun angles get shallower and shallower in the winter, the sun actually comes through and it heats up the building when you want it. So it works really well. And instead of putting like a solid panel in there, we put in this laminated glass that's got photovoltaic cells in it, so it also generates electricity. So that's why you see this kind of interesting grid pattern on the floor. We put tons of insulation in the roof and ceiling. The structural engineer specified 50% fly ash mix in the concrete, which allows them to put less concrete in, which, like I said, that's a big generator of carbon dioxide when they're actually burning gypsum to make cement. It allows them to put less cement into the mix. And also, it takes longer to cure, but it's stronger. And then we put drought-tolerant landscaping. That doesn't save us any energy. But in fact, if you could reduce water use, turns out in California, something like 20% of the electrical energy generated in California goes to pumping water around the state. So the water in San Diego actually is coming from Northern California. They pipe it all the way down the state, over the Tehachapi Mountains, down into Los Angeles, and all the way down to San Diego. So these are the mechanical concepts that we used in this building. And again, I won't go through all of them, but I'll flip through a bunch of them. So the most important thing we did was we put in radiant floor. So do you guys all know what that is? So you actually pipe water through the floors and you heat up the floors and the floors become warm. So it's really weird. So you're used to thinking that comfort is based on air temperature, and air temperature, the magic number is like 72 degrees, something like that. But in actual fact, that's not totally true. So comfort depends on radiation, it depends on air movement, it depends on air temperature. And so if you're using radiant floors, actually, you can start playing around with the actual air temperature and it still feels comfortable. So the great example of this is this building has actually got radiant heating and cooling. So in the summer, we actually cool down the floor. When I first moved into the building, like the first month we were there, it was August. It's like 95, 100 degrees, something like that. And I'm sitting in my office and it feels kind of cool, kind of like it feels in here right now, kind of about this temperature to me. And I was thinking, it's a little cool in here. And the mechanical engineer that kind of was commissioning the building comes walking through with a thermometer and he's going, wow, this is really amazing. So I said to him, what's amazing? And he said, it's 78 degrees in here. And I said, nah, it can't be 78 degrees. I'm freezing my butt off in here. And in fact, it was 78 degrees, and it was because the radiant floor was in cooling, and it was essentially sucking the heat out of my body, and I felt cold. And so the interesting thing is, you know how everybody's got, like, you know, some people feel warm and some people feel cool in the same room? So, you know, we have that in our office too. So the people that, like, on a warm day, the people that feel cool, they take their shoes off. And there's something about the palms of your hands and the soles of your feet. I actually heard something about in sports medicine, they're like making special gloves to cool athletes off really quickly. That if your feet touch something cool, it'll pull heat out of your body really quickly. And so if somebody feels warm, in my office, they'll just take their shoes off and walk around with it in bare feet for a couple of minutes, and then it'll cool them down. So I got people at, that's their excuse at least. And then the other thing we did was what's called a ground source heat pump. So do you all know what a heat pump is? Kind of? Some of you do. You're architectural engineers, of course you guys know. Do the rest of you know what a heat pump is? You know what an air conditioner is, right? So a heat pump is like an air conditioner that you can run forwards and backwards. So instead, an air conditioner takes heat out of a room and dumps it outside, right? So an air conditioner or a heat pump, it can take heat out of a room and dump it outside, but it can also take heat of outside and dump it in the room. So it's like a reversible air conditioner. And this heat pump, instead of going air to air like an air conditioner does, it goes water to water. So there's kind of a loop outside in the ground, and there's a bunch of loops, 5 different zones inside poured into the floor slab. So either it's pulling heat out of the ground and dumping it in the room in the winter and warming up the floor in the room, or alternatively in the summer, it's taking heat out of the floor slab and dumping it into the ground. And the nice thing is, if it was an air conditioner, a lot of times you're trying to take heat out of the room and dump it outside, but it's like 100 degrees outside, so the thermodynamics don't work that well because you're trying to dump heat into 100-degree air and the heat transfer doesn't work that well. But the ground stays roughly 57 degrees, 58 degrees in that range, so it's a lot more efficient dumping that heat into 57-degree ground than it is into 100-degree air. And then the other thing that's really slick that they did was, this is the heat pump here. So this does all the heating and cooling for the building. It's like, if it was sitting on the ground, it's about this tall and about this wide and about that long. I mean, it's like a big filing cabinet. That's how big the whole thing is for a 7,000 square foot building. And they set up this system that they skim some waste heat off of the process and they dump it in this tank. So this isn't like a hot water boiler. It's just a storage tank with insulation around it. And that's our hot water. So they don't even generate we don't have like a boiler for hot water, which is a great idea, except there's 2 problems. The first problem is it's not hot water, it's warm water, because it's just skimming off some waste heat, which is fine actually, because we don't take showers or baths with it, we just wash hands with it, so that's cool. But that's not the real problem. The real problem is in the spring and the fall, half the time you're not running you don't need air conditioning or heating, so it's not running. So if it doesn't run, for half a day, guess what happens? The hot water is cold water. So it's a good idea, but it's not perfect. The one thing we did put in after the fact is one of those little instantaneous heaters that serves out boiling water. So if you want like coffee or tea, you can get hot water that way. And then we have natural ventilation in, so we have operable windows, and then along the south side of the building, there's this whole series of sliding glass doors that on a nice day, people just open it up and let the air flow in and out. Our ventilation air, since we're not air conditioning the building, we use the radiant floor to condition the building. It's just purely for ventilation air, not for conditioning. So we bring the air in, temper it to about 72 degrees, and just dump it into the space. And the nice thing about that is there's no recycled air. It's just fresh air coming in, and then an equivalent amount of air gets exhausted out. And there's actually studies that show that that's a much healthier way of ventilating. There's less transmission of colds and things like that. And then that's a waterless urinal there. So we have a waterless urinal in the men's room. We have all the toilets are these, they're called dual flush low flow toilets. So there's like a solids and a liquids button. And then we got these cool faucets that you've seen them before. They're sensing. They sense you and they turn on, and they have like a shower head sprayer, so it uses less water. But on top of all that, if you could see on the top, it's got this little photo sensor, so that's where it gets its energy. There's no power attached to it. It just uses, takes the light energy in the room and converts that to electricity to control the sensor. So it's pretty cool. And then electrical things, we're electrical engineers, so this is where we went really crazy. And like I said, part of this, the idea was it would be a lab for us so we could try stuff out and measure things and test things. So we put all these different systems in just partly to save energy and partly to be able to compare how things perform. So the first thing is, of course, high efficiency lighting. So every light except 4 in the building are either fluorescent or what are called induction lamps, which is very similar to a fluorescent system. So very high efficiency and long life. Then we came up with this idea that we're doing something called a task ambient system. And the idea there is you put in less overall light in a building, so just kind of enough light that you could see to walk around and function, and then put in additional light just where you need it on the work surfaces where you're going to be working. So you're kind of just putting the light where you need it instead of everywhere. And it's a much more efficient way to design. Now, so the idea was, you can see right there, we're going to have these desk lamps in. So I told my staff, look, we designed this task ambient system. IES recommends 30 to 50 foot candles for office spaces. We're putting in 17. And so I don't think when it gets dark during the day, it's no problem because the building's daylit and you got plenty of natural light. But at night, once the sun goes down, it's going to get too dark. You're going to need more light. So if it's too dark for you, let me know. We'll go out and find some nice fluorescent desk lamp or something like that, or an LED desk lamp, and buy it for you guys, and you can use it. Nobody ever asked for a desk lamp, and people work late at night a lot of times. And I couldn't figure it out at first, but I think what's going on is that you could see the buildings, like everything's light colored. So we went out and we found the whitest, highest reflectance paint we could find. It's about 90% reflectance. And the ceiling is 80% reflective acoustical ceiling tile. And you can see the desktops are maple, so they're pretty light, and the floors concrete, but it's a pretty light colored concrete. So everything's pretty light colored. So what happens is at night, 2 things happen. One is it's nighttime. You can see out the window. You can see it's nighttime. So your kind of psychological expectation for light levels goes down a little bit just because you could see it's night outside. And then the other thing is because all the surfaces are so bright, even with less light in the space, it still appears really bright. So I think what's going on is just people, it seems bright, so they don't think they need light, so nobody's ever asked for light. So I do have one of these on my desk, but it's a sample that a firm gave me just to test out, not because I actually need it. And then we put in all kinds of lighting controls. That some of them are put in kind of side by side so we can compare one to another. So we've got everything, a number of different kinds of occupancy sensors. Some of them are ultrasonic based, so they're sound based and they look for Doppler shift. Some of them are passive infrared, so it's kind of looking out in a pattern and looking for motion across a pattern, infrared motion across a pattern. Some of them, like this one right here, is actually built into the light fixture, so they're like on board on a suspended light fixture. We've got daylight sensors in the light wells. We've got other daylight sensors that are built into the ceiling, looking down into the room instead of up into the sky. We've got kind of sensors that'll dim the lights down. controls that work the best in our building are actually, for the most part, the simplest ones. So this just gives you an example of, these controls are all working together to control those light fixtures down here. So it's a daylight photocell, it's an occupancy sensor, it all goes back to a lighting control panel, and then it controls these lights here. This is a occupancy sensor with a daylight sensor and also a time clock that are working to control this light outside. So kind of we combine things to try to shave a little bit more energy out of each one of those things. And then, of course, like I said, we turn off the lights if there's enough daylight. So this graph here shows all different light sources, electric light sources in red, and how much light you get for, sorry about that, how much light you get for the amount of energy that you use. And you can see those two yellow bars on the end. That's the shorter one is unfiltered sunlight. The taller one is sunlight if it's been kind of filtered through this really good glass that screens out a lot of the heat. And so what that represents is not the amount of electricity used, because sunlight doesn't use electricity, but it represents the amount of heat you're going to get for the amount of light that you get. So an interesting thing is that architects and engineers, and mechanical engineers and electrical engineers, when we try to make buildings really efficient, you focus on HVAC and you focus on lighting. But in actual fact, buildings don't just use energy in those two areas. There's actually three main areas where we're using energy. So one's HVAC, one's lighting, but the third one is on plug loads. So that's your computers, your refrigerator, your dishwasher, all those types of things. And so, but architects and engineers always go, I can't control that. I just put the plugs in the wall, and I can't control what the tenant comes in and plugs in. If they want to bring in a 200-watt halogen uplight, I have no control over that, which is somewhat true. So that's what I always used to say too when we were designing buildings. But this was an exception because I own the building and we're the tenant. And so this is the one time I could control what gets plugged in because it's my employee. So we decided we're going to take a really good hard look at this and see if we can learn anything. So first thing we did is before we moved out of our old building when we were still in design, somebody took everything that we owned that you could plug in and plugged it to a meter and measured how much energy it used. And we learned some really interesting things. So the first thing we learned is, the old CRT screens use like 3 times as much energy as a flat screen monitor. So we agreed when we moved, we're going to buy everybody flat screen monitors and donate our old computer screens to a local school. And then another thing that we decided we're going to try out is there's this company that makes a plug strip that's got an occupancy sensor that plugs into it. And the way you use it is you put the occupancy sensor under your desk, and the thing, it wouldn't work here because you got to make sure that it's screened from seeing like other parts of the room. But in most cases, it's like a filing cabinet or something. So if you put it by the filing cabinet, it just sees your cubicle. And if you get up and walk away, it'll turn off kind of the bottom row of plugs on that plug strip. So we decided that we're going to get a bunch of them and put them in. So this is another one of those things that didn't work out the way I thought it would. So when we moved in, what we found out was that first thing is nobody wanted task lamps, so we didn't have any use for the task. So they didn't have task lamps to plug into it. The next thing is, you guys know this, but us older guys don't know this. Nobody uses stereos or anything like that, things like that anymore. They just stream it off the net. It's like a headphone into their computer. So there were no stereos to plug in. So it's basically, the only thing that people were plugging in are the computers, which you can't switch off when you walk away. You're going to crash your computer. And phone chargers, which you can't turn those off, otherwise you come back and your phone's not charged. And then, so the only thing realistically that we might put on there is the computer screens and those have sleep modes, so you can save a little bit of energy, but it's actually pretty minimal. So we're using these in a couple of places, but not much at all. The other thing that we found that was really interesting is the other place where we're eating a lot of energy is on, do you guys know what phantom loads are? Yeah? So, no, some of you yes, some of you no. So phantom loads are, your microwave oven's a phantom load. So you, even when you're not microwaving, the thing's got a little LED that's glowing, so it's pulling electricity, right? So like, I measured I have like an old TV, kind of like one of these things at home. That is using 30 watts, 24 hours a day, 7 days a week. Does anybody have TiVo? I don't have TiVo, right? Nobody has TiVo? You don't have any like filthy rich college students here? Yeah. So one of my staff has a TiVo. I don't have a TiVo, and he took it home just for kicks and plugged the little watt meter thing into his TiVo. It's 120 watts, 24 hours a day, 7 days a week it draws. Unbelievable. So the worst thing we found was this printer here. This is a laser plotter, it's called. It's for printing large-scale drawings. 30 watts, 24 hours a day. So when it's in standby, it's using 30 watts. So obviously, if I got to buy photovoltaics to offset all the load for this building, 30 watts, 24 hours a day is pretty irritating. So, we talked about, we could turn all our printers off. So, my partner goes, yeah, we're going to tell everybody when they leave, they got to turn the printers off at night. And I started laughing. I was like, yeah, that'll work for like 20 days or so, and then, everybody will forget to do that. So, we're trying to think, what can you do? You can't really turn the printers off during the day because it takes so long for them to boot up that it's a pain in the neck then when you want to print something. So you have to leave them on all day long, but you don't want to leave them on all night long, and there's absolutely no reason to do that, but how do you turn them off? So the idea that we came up with is you can buy these remote control circuit breakers, and they don't cost that much money. You don't need that many anyway. And if you wire them to your security system, when you set the alarm on your security system, it'll flip off the breaker for you, and you don't have to remember to flip the breakers off. So and the funny thing is, my staff is really good at setting the alarm on the security system. So like, one day a guy came in on a Saturday. When he left, he didn't lock the door, but he remembered to set the security system so the building, the door is unlocked all weekend long, but he remembered to set the security system. So that's actually a good way to do it. And what that would do is it would turn the power off, the phantom load off on these printers all night long, every night, plus all weekend long. So it's a fairly significant amount of power. And then the last thing you do is you do everything you can do to get the energy consumption down, and besides the photovoltaic system that will offset the energy consumption for the building, and that we calculated as being slightly under 30 kW. So here's some of the lessons learned were, try to keep it as simple as possible. If you have complex controls, it makes the commissioning really complex. We've been in the building about a year now, and there's still things that we're trying to, get fixed and get installed and get working right. We ran into some really interesting issues with the city planning staffs because they had never seen buildings like this before. And in fact, the fire department's been out to my building like 4 times now. And the most recent, I came driving in one day and they had a ladder truck out there. And the ladder fully extended like twice as high as my building. There's a guy up on top of the camera taking pictures of the roof because they're doing some tapes and videos for the San Jose Fire Department. It turns out that's a huge issue because think about it, if you're a fireman and there's a fire during the day and you go up there with your axe and start chopping holes in the PV panels, you get electrocuted. Or you could get electrocuted. if another thing we found is if there's things that we could use for two purposes, and a lot of times that'll help justify the cost if it's something that's pretty expensive. But sometimes using things for two purposes gives you unintended results, like that heat pump hot water system that I was talking about. So the system generates about 54,000 kilowatt hours a year. That's what we've calculated it to generate. The building is approximately 60% below kind of the ASHRAE standards for current. Actually, this is in the 1999 standards because this building's a little older. And the PVs are sized to generate net 100% of the load. So here's the cost information. So PVs cost anywhere from $8 to $10 a watt installed. So this system we think was about $8.50 a watt, which is about $255,000 cost. But California gives us a rebate if we put PVs in. So that rebate was it's about $2.60 a watt. And that's gradually going down as they pay more and more money out. And then the choice that we had was we could either just take the money and run, or we could pay tax on that money. And if we paid tax on that money, then we could use the full $255,000 and you get a 30% tax credit on the full value. The alternative was to reduce that by the rebate and then get 30% of that as a tax credit. So we decided we're going to pay tax on it, take 30% of the full value, and then also accelerated depreciation. What that means is, from an accounting standpoint, you could say the value of my system goes down to 0 over 5 years. And I can use that as an expense for my business. And therefore I don't have, if you have an expense, you don't have to pay tax on the money you spent on it. So our calculation for the value of this, or the cost of the system after 5 years, this is not doing like net present value, it's just a simple add the numbers together after 5 years, was about $49,000. So we had to pay $255,000 up front, but after 5 years, it's going to only end up netting out to less than $50,000. And so energy, somebody told me your energy here costs like 4 cents a kilowatt hour. Just ridiculous.
More like 5.
Oh, okay, 5. Expensive. So we're paying about 15 cents a kilowatt hour, so like 3 times what you're paying. And so our payback's about 7.1 years for the system, which is good because it should last at least 20 years. And then the other thing we tried to do, and this is very rough numbers, but we tried to look at how much does this system cost compared to a normal, if we had just done this building as a normal remodel and done the same building but not put all the things that we put in to try to really crank the energy, use energy consumption down and not put in the photovoltaic system. And we ballparked the numbers at about $204,000 of additional cost. And then when you add in kind of the architects and engineers' fees and all that stuff compared to that, it comes in at about almost $250,000, which is a lot of money, but when you compare it to the overall cost of the building, and these numbers, if you kind of run the numbers as $1 per square foot, they look ridiculous, but it's because we're in California and everything's ridiculously expensive in California. But it's about a little over 6% of the total value of the building, which, considering what we've been able to do, is I don't think is excessive, put it that way. And then the architect at one point asked me to do a CO2 calculation to kind of talk about what's your carbon footprint. So this was our estimate of kind of what our CO2 use was in our previous building before we moved into this building. Now, this is interesting. Take a look at this. So that's the before. this is the after. So great, you know, we're down to 0 here. But see this number 52,841, right? Out of 93,000. So turns out over half of our CO2 is like me flying out here, burning carbon dioxide on an airplane to get out, or burning gas on an airplane flying out here. So yes, that's the other lesson, is that you know, even though buildings are about half the problem, you know, transportation is the other half of the problem that you got to pay attention to. And so, you know, we need to be finding solutions for transportation. So one of the things that we as a company are starting to look at seriously, both for ourselves and also for our clients, is this idea of video conferencing. So can I, instead of flying to a meeting, can I video conference into a meeting using a T1 line and a video conferencing setup that's you know, there's systems out there now that are like, you know, $10,000 to $20,000 that can actually do that. Oops. So, you know, how do you do it? The one thing is you got to have a client that's willing to take risks. So, you know, since I was a client, that was an easy one. But if you're designing a building, it's not always that easy. And you know, not everything's working perfectly. Afterwards, I could talk to you about it. But you know, there are the things that we chose to put into that building that were, quote, cutting edge, but there's a very fine line between cutting edge and bleeding edge. So some of the things don't work perfectly. And you have to have, I think it saves a lot of pain to have a team that actually knows how to do these types of projects, because they're done a little bit different than normal projects. And you got to kind of get the whole team together on the same page, working in the same direction and talking to each other from day one when you start the projects. And then there's this mantra that they always say, before you size like a renewable energy system, be it a windmill or be it a photovoltaic system, first reduce your energy consumption as far as you can possibly reduce it, and then size your system. The two things that really helped us save energy in our case was the daylighting and the use of radiant floors in the building. And then in our case, we walked away from the LEED rating until we were basically done the project. Then we went back and said, oh, by the way, you know, what's this going to add up to? And we still haven't submitted, but it looks like we have a shot at gold, but it could be silver too. So, you know, one of the things is that if you look at the statistics, every time I see new statistics, it looks uglier and uglier as far as kind of what's going on with global warming. So, you know, at first I was like, I don't know if this is real, and then gradually as time's going on, not only am I convinced, but I'm getting more and more worried about things. So, you know, this is, and the U.S. is U.S. and China are the two worst transgressors in the world. And the difference between the U.S. and China is China's got a lot more people than we do, and we're still making just as much CO2 as they are. I think they just passed us in the last year. So it's really, I think, up to the U.S. to lead in trying to, you know, reduce CO2 production and try to get things. You know, it's not even a matter of getting things under control. It's getting things, try to keeping things from getting catastrophically out of control. So that's it. Any questions?
Questions, comments?
How much water does it take to do the heating in the floor and all those pipes out your guys' under your parking lot or out there in the landscape?
Now, I don't know, but it's a closed system, so it's not constantly using water. You kind of charge it up, and it's just the water in the pipes and just cycles around. So there's not like a connection to a hose and they keep pumping more water into it.
So would you be able to tell if you got a leak?
Yeah,
your system
I think the system's got some sensors in it that I could tell. And the other thing is, if we had a leak and it all either the stuff outside or the stuff inside the depth, I would know because something we won't have air conditioning anymore. And the building has to start getting either really warm or really cold.
Yes.
I noticed you guys didn't mention anything about a gray water collection system. Do you guys not have enough rainfall for that to be worthwhile?
Good question. So the question was about, should I be reading the questions?
That's fine.
Okay. The question was about gray water. Do we have a gray water system? The answer is no. And it's not, gray water where we are isn't so much about rainwater collection. We actually do those systems sometimes, but it's kind of dumb in California because you need a massive, expensive tank because you get all your rain in the winter, and then you get no rain at all from April to October or something like that. So in order to collect the water and use it, it's ridiculous. So the way they do gray water in California is collecting water from like showers and bathtubs. So I'm actually putting one in my home, but it's not collecting rainwater at all. It's collecting shower water, bath water, sink water in the bedrooms, not the sink water from the kitchen. And you can only, there's rules about how long you can store it. So essentially what happens, it goes into a tank and immediately gets pumped out into the landscaping. But if you think about it, in an office building, nobody's taking showers, nobody's taking baths, and the sink isn't used all that much, and you can't use the toilets. So there's very little water that would have been useful for a gray water system.
Do you store any electricity generated by your
No,
solar system?
that's a good question also. So the question is, do we store the power? So there's two ways you can do this. By far the most common way is what's called a grid-tied PV system. So basically, you just, you generate your electricity and you just plug it in, and most of the utility companies, they're starting to loosen up on this, but generally they want you to plug in right at the switchboard, which is no problem for us because it's a small site and it's all right, conveniently located. So you plug it into your switchboard, and basically now it's just part of the electricity in the building. So if the building's not using it, it just flows backwards out onto the street, and the meter spins backwards. And then if you need it later on, the meter starts spinning forwards again. So essentially, we're using the grid as our battery. If we have extra power, we dump it out, and it's not really stored, it's used by the grid. And then at night, when the system shuts down, then we start pulling off the grid. The other way you do it is you put a battery system in, and then you store it in batteries. And we have a house under construction that they wanted to set it up that if they had a really bad earthquake, we also happened to design it's a small town right behind Stanford University, and it's right on the San Andreas Fault. Literally, I can throw a rock from their town hall and hit the rupture zone of the San Andreas Fault. Talk about bad placement. This family wanted to design their house that it could actually be a community resource if there's a really bad earthquake event. So they have a system that actually it can disconnect from the grid, store the power on batteries, and then they could have power 24 hours a day, as long as they don't go too crazy with what they're plugging in. But their system's oversized anyway, because in addition to sizing it to run the house, they size the system to charge 2 electric cars. So they got lots of power there. And they also put in like a natural water swimming pool so they can use it for drinking water if there is a major earthquake event. So that's pretty amazing. So that's the other way you do it. And I would argue that my way is better because if you think about it, one of the problems with batteries is they have about a 10-year life, and then you got to dispose of them, and they got lead and other hydrochloric acid and stuff in them. Also, if you think about it, I'm generating too much electricity during the day because I need to be able to pull some electricity back during the night, and it's got to net out to 0. So if I'm generating too much during the day. Well, when does the system overall, when does the grid use the most electricity? 3 o'clock in the afternoon on a hot day in summer, when the air conditioners are cranking and all that stuff, that's when they have all the power plants fired up, and they're using dirty power that they're importing from Nevada from coal-fired power plants and stuff like that. So by giving my electricity away to my neighbors to use, I'm actually reducing the amount of dirty power that's being imported. And then at night, a lot of that power is very clean because they have hydro and stuff like that they're running at night. So the power at night is actually cleaner. So I'm displacing dirty power, and then when I take power off the grid, I'm taking clean power. So I would argue that it's environmentally more beneficial to do it that way than to actually put a battery system in.
Okay. Yes.
I was wondering if your demand is a lot less during the winter for your geothermal. Like when it's 57 degrees, like in the earth, is it not too much temperature difference? Heat transfer?
That's an interesting question. So the question is my demand lower in the winter or the summer for the geothermal system? No, I don't know for sure, but I mean, one of the things about the air conditioning is inherently a little less efficient than heating with a heat pump, because when you're heating with a heat pump, I think that electric energy actually, some of that becomes heat. So that's one issue. The other issue is that the answer is I don't know. The real answer is I don't know. But the other issue is that in the summer, it's hot during the day, and sometimes it's very hot, so we're running the air conditioner. But then at night, it usually cools off. So it takes very little energy to keep the building cool in the summer at night. But in the winter, at night, you're heating during the day sometimes, and then you're heating even more at night. So I really didn't know exactly what the balance is. I'd have to actually look at the energy model to tell you for sure.
Okay, well, thank you very much.